Welcome to Deep Dive into Knowledge.
How Earth became our only living world.
Hello, and welcome to Deep Dive into Knowledge. I want to begin with a word that I think we often misuse, miracle. Usually when we use that word, we're reaching for something religious, aren't we? Something divine, an intervention from above that sort of breaks the rules of reality. But I've been thinking about the contradiction hiding inside that word. The true miracle isn't a violation of the natural laws. It is, in fact, a statistical and chemical reality. It's the result of the laws of physics playing out in a way that is so improbable, so precarious, that it just defies our ability to fully comprehend it. I mean, just consider where you are right now. You might be sitting in a chair or walking down a street. You feel still, you feel grounded. And yet you're standing on a ball of rock and metal. You're spinning at 107,000 kilometers per hour around a burning star. You're wrapped in this terrifyingly thin layer of gas that allows you to breathe. And you're composed of stardust atoms forged in the hearts of dead stars that has, over billions of years, organized itself into a form that can think, that can wonder, that can look back at the universe and ask, how did I get here? That transition from a chaotic cloud of dust to a mind capable of asking that question, that's the only true miracle I know.
It is a staggering thought, isn't it? When you stop to truly feel the weight of that motion, the sheer velocity at which we're traveling through the void, the stillness of our daily lives feels like a magnificent illusion. And you're right about the scale of the story. We're talking about a biography that spans 4.6 billion years.
It's almost impossible to grasp.
It is. It's a narrative of chaos turning into consciousness, a story of fire, of ice, of bombardment, and of a resilience so profound it's almost frightening. We look at the Earth today, the blue oceans, the green forests, the cities, and it all feels so permanent. It feels inevitable. But when you look at the history, when you really trace the timeline from the very beginning, you realize that nothing about this was inevitable at all.
It feels like we're walking a tightrope, and we've been walking it for billions of years without falling off.
That's a perfect analogy.
I suppose the intent of our conversation today is to really understand that journey, to try and understand why, out of the trillions of planets that likely exist in the universe, this one exists. Why is this the only one so far that we know carries the burden and, I suppose, the privilege of life?
That is the question, isn't it?
Okay.
And to answer it, we have to go back. We have to go back before there were oceans, before there was rock, before there was even a sun. We have to go back 4.6 billion years to the birth from nothing. Although, as we know, nothing is a bit of a misnomer in space.
It wasn't really empty.
Not at all. It was a massive drifting cloud of gas and dust, what we call the solar nebula.
I've always found that concept quite difficult to visualize. We say gas and dust, and I picture the dust under my sofa or the steam from a kettle. But we're talking about something on an entirely different scale, aren't we?
We are. I mean, imagine a cloud that is light years across. So vast. It's almost incomprehensible. And there's something quite poetic about what that dust actually was.
Yeah.
It wasn't just random matter. It was debris. It was the leftovers of previous generations of stars that had lived, burned through their fuel, and died in massive explosions.
So all the raw ingredients.
All of them. Every atom of carbon in our bodies, the iron in our blood, the calcium in our bones, it was all forged inside those previous stars.
So when people say we are stardust, it isn't just a romantic sentiment. It's a literal description of our chemical composition. We're the ashes of dead stars.
Precisely. We are the recycled remnants of a violent cosmic past. So you have this cloud just drifting for millions of years, and then something disturbs it. It could have been a supernova nearby, sending a shock wave through the gas, or perhaps gravitational waves from colliding objects. But that disturbance was the catalyst. It caused the cloud to start collapsing inward.
And once that collapse begins, gravity just takes over, I assume. I understand that gravity pulls things together, but why did it start spinning? Why didn't it just clump into a big ball in the middle?
That is where the physics gets really interesting. As the cloud collapses, any tiny, almost imperceptible rotation it had gets amplified. The best way to think of it is an ice skater spinning on the spot.
Right, with their arms out.
Exactly. When they start, their arms are out, and they spin slowly. But as they pull their arms in tight against their chests, they speed up dramatically. That's the conservation of angular momentum. The solar nebula did the exact same thing. As it collapsed, it pulled its arms in, and it spun faster and faster and faster.
And that spinning is what flattened it out, a bit like tossing pizza dough.
That's a great way to put it, yes. The centrifugal force flattens the cloud into a disk, The center, where the pressure and density were highest, became incredibly hot. That pressure eventually ignited nuclear fusion, and our sun was born. But the sun isn't the whole story. It took the lion's share of the material, of course.
How much are we talking about?
Almost everything. 99.8% of all the material in that cloud went into making the sun.
Wow.
But there was a remainder, the leftovers. That tiny fraction of 1% formed a spinning disk of dust and gas around the new star. And that fraction, that's where we come from.
It's humbling to think we're the 1% of the leftovers. We're the cosmic scraps. But I still struggle to get from dust to a planet. Dust doesn't just stick together. If I blow dust into the air, it disperses. How do you get from a cloud of microscopic particles to a boulder, let alone a planet?
That's one of the biggest hurdles in planetary science. And you're right, gravity doesn't work well on tiny dust grains. It's far too weak.
Yeah.
So in the beginning, it was likely electrostatic forces.
Like static electricity.
Exactly like that. Think of dust bunnies under a bed, how they clump together. The dust grains in the solar nebula bumped into each other and stuck, held together by that same static charge.
So the Earth literally started as a cosmic dust bunny.
In a way, yes. A very, very big one. These clumps became pebbles. Pebbles collided and became boulders. And once you get to the size of a boulder, say a kilometer across, then gravity becomes strong enough to start pulling other rocks in. This is the process of accretion.
And it must have been violent.
Incredibly violent. It's messy. Rocks smashing into rocks, generating immense heat with every impact. And through this chaotic, violent process, around 4.6 billion years ago, one of those growing masses became the early Earth.
But we shouldn't picture the blue marble we see from space today. If we could time travel back to that moment, what would we actually see?
If you were to look at Earth 4.6 billion years ago, you wouldn't recognize it at all. Geologists call this period the Hadean Eon.
From Hades.
From Hades, the underworld, and it's entirely appropriate. It was a molten nightmare.
Just how hot are we talking?
The surface temperatures were over 1,200 degrees Celsius. There was no solid ground to stand on. It was just a magma ocean, churning and boiling under a toxic sky.
And the atmosphere.
Well, if you could call it that. It was a poisonous mix of hydrogen, helium, methane, ammonia, and volcanic gases. It was a place where absolutely nothing we know could possibly survive.
And on top of all the heat coming from the planet itself, it was being battered from above.
Relentlessly. We are still in the very early days of the solar system, so there's debris absolutely everywhere. Meteors and asteroids were constantly slamming into the surface, adding more heat, more kinetic energy to the system. It was a true fireball.
It sounds completely inhospitable.
It was. But amidst all this chaos, something crucial was happening deep inside the planet. A process we call the Iron Catastrophe.
That sounds ominous. Catastrophe usually implies something going terribly wrong.
In this case, it was a catastrophe for the uniform structure of the planet, but it was essential for our future. Because the planet was liquid, the heavy elements were free to move. Specifically, iron and nickel. Being heavier, they sank through the lighter magma, falling toward the center of the planet under gravity.
While the lighter stuff floated up.
Exactly. The lighter silicates and rocks floated upward. This process, called differentiation, is what gave Earth its structure. The dense iron core, the molten mantle, and the beginnings of a crust.
So the Earth organized itself. The heavy stuff went to the middle. The light stuff stayed on top. But why does having a ball of iron in the center matter to us now? I can understand the solid ground, but what does the core actually do for us?
That spinning iron core is a generator. It created a dynamo. It generated a powerful magnetic field that reached out from the center of the Earth far into space. And while that didn't matter much to a ball of lava billions of years later, that invisible shield would become our most important defense.
Against what?
Against the sun. It protects our atmosphere and the surface from deadly solar radiation, the solar wind. Without that iron sinking to the center in the beginning, the solar wind would have stripped away our atmosphere over time, just like it did on Mars, and life on the surface would be impossible.
So even in that hellish beginning, the foundations for a habitable world were being laid?
Deep inside, yes. So we have a structure, we have a core, a mantle, but we still have a ball of lava. We need to cool it down. I imagine this took a very, very long time.
We used to think it took 500 million years or more for any kind of solid crust to form. But the science on this has shifted recently, hasn't it?
It has, quite dramatically. We found evidence, these tiny, incredibly resilient crystals called zircons in Western Australia. that date back 4.4 billion years.
4.4 billion, that's incredibly old.
They're the oldest piece of Earth we have ever found. And they tell us that solid rock existed on the surface much, much earlier than we previously thought.
And these zircons revealed something else, didn't they? Something about water.
They did, and this was a real shock to the geological community. The chemical signature of these ancient crystals suggests they formed in the presence of liquid water.
What's so early?
It implies that Earth might have had oceans, or at least some liquid water on its surface, just 150 million years after it formed. That's within the first 3% of the planet's entire lifetime.
That completely changes the picture. We go from hell on Earth to a potentially watery world much faster than anyone assumed. It suggests the planet was trying to become habitable almost immediately.
It certainly seems that way. But just as things were starting to settle, just as the crust was beginning to form, we faced the biggest catastrophe of all, the impact that gave us the moon.
The Theia impact. This is perhaps the most dramatic single event in our entire history. Around 4.5 billion years ago, when Earth was only about 100 million years old, a protoplanet roughly the size of Mars, we call it Theia, was on a collision course. I just want to pause on the scale of this. A planet the size of Mars. We're not talking about an asteroid like the one that killed the dinosaurs. We're talking about another world hitting us.
Yes. Imagine looking up at the sky and seeing a planet getting larger and larger until it fills the entire horizon. It's slammed into Earth at something like 40,000 kilometers per hour. The violence of that event is hard to even conceptualize.
It wouldn't just leave a crater.
No, a crater is what happens when a rock hits a solid surface. This was planetary destruction. It likely vaporized Theia completely, and it melted Earth's surface all over again, turning that newly formed crust back into a magma ocean.
So it was a complete reset.
A total reset. Vast amounts of debris, molten rock from both Earth and Theia were blasted into orbit. If you had been looking at Earth from a distance then, you'd have seen a ring of molten rock encircling the planet, glowing red-hot against the black of space.
Like Saturn, but made of lava and fire.
Exactly. And over millions of years, gravity gathered that debris together. It coalesced, clumped up, and eventually formed the moon. We've confirmed this recently, actually. Analysis of lunar rocks brought back by the Apollo missions shows they match Earth's mantle almost perfectly.
So the moon isn't a stranger. It's made of us. It's born of Earth.
It is. And this wasn't just a cosmetic addition to our night sky. The collision fundamentally changed how Earth operates, didn't it?
It engineered the planet for life. First, the impact was off-center, so it knocked Earth onto its side. It gave us our 23.5-degree axial tilt. That tilt is the reason we have seasons. Without it, the equator would be perpetually burning and the poles frozen solid with no variation throughout the year.
So it creates more varied climates.
It does. And secondly, it sped up the Earth's rotation significantly. Back then, after the impact, a day was only about 6 hours long. That's incredibly fast. The weather must have been ferocious, constant high winds.
Indeed. But over billions of years, the moon's gravity has been pulling on Earth, acting like a brake, slowing our rotation down to the 24 hours we have today. And that braking action leads to the most critical part. The moon acts as a stabilizer.
What do you mean, a stabilizer?
The moon is quite large relative to Earth, much larger than most moons are relative to their planets. Its gravity acts like an anchor. It stops Earth from wobbling erratically on its axis. Without the moon, Earth's tilt could swing wildly over millions of years, from 0 degrees to maybe 80 degrees, causing absolute climate chaos that would make the evolution of complex life very, very difficult. The stable climate we enjoy is, in many ways, a gift from that collision.
So we have a moon, we have a cooling crust, but we still need the oceans. We mentioned the zircons hinted at water, but to get the vast global oceans we have today, surely we needed more than just what steamed out of the rocks.
That's right. And this leads us to the next violent chapter, the Late Heavy Bombardment. Between about 4.1 and 3.8 billion years ago, the solar system was still clearing out its leftover construction debris. The orbits of the giant planets, Jupiter and Saturn, were shifting, and that huge gravitational dance flung asteroids and comets from the outer solar system towards us.
It just seems cruel. Every time the planet tries to heal, it gets smashed again.
It does seem that way.
Mm-hmm.
But this bombardment was a blessing in disguise. You see, Earth formed very close to the sun. It was too hot in this region for water to condense into liquid during the initial formation. Earth should have been a dry planet.
So the water had to be imported.
It had to be delivered by cosmic trucks. Comets and asteroids from the outer solar system, specifically the icy ones, are full of water ice. When they smashed into Earth, they vaporized, releasing enormous amounts of steam into the atmosphere. They brought trillions of tons of water.
And not just water.
And not just water. They also brought organic molecules, carbon compounds, the very building blocks of life.
There's a recent insight on this that I found absolutely fascinating. The idea that some of this water is actually older than the sun itself.
Yes, that some of it originated from interstellar ice clouds that existed before our solar nebula even formed. It means the water in your glass isn't just from our solar system. Some of it literally predates the solar system. It's truly ancient.
So the atmosphere is filling up with steam, the planet is finally cooling down enough, and then the rain begins. I've tried to imagine this event, the Great Rain. It wasn't a thunderstorm like we have today, was it?
No. It's on a scale that's hard to fathom. Around 3.8 billion years ago, the surface cooled to below the boiling point of water, and the skies opened. Imagine a global storm that lasts for 2 million years.
2 million years of rain.
The sky is dark gray, completely choked with thick clouds. The sun is blocked out. Lightning is cracking constantly because of all the volcanic ash and static electricity. And the rain falls in sheets, hot rain filling the basins, filling the cracks, covering the lowlands. It was a deluge of biblical proportions, but playing out on a geological timescale.
And when the clouds finally broke?
When the clouds broke, Earth was a water world. By 3.5 billion years ago, the planet was almost entirely ocean. There were no continents yet. Not really. Just chains of volcanic islands, like a global version of Hawaii poking up through a single planet-spanning sea. We know this because of pilobasalt's lava rocks that have a distinct shape that only forms when lava cools underwater. We find them from that era all over the world.
And in this global ocean, in this chemical soup, something happened that has never been explained fully. The spark. Life. This is the part that always feels the most miraculous to me. How do you go from dead chemistry to something that is alive?
That is the greatest mystery of them all. For a long time, we thought life began around 3.5 billion years ago. We found stromatolites, fossilized mats of bacteria from that time in Australia. But as we keep looking, we keep pushing that date back. Recent findings are suggesting life could have begun as early as 4.1 billion years ago.
Which is startling. It implies that life began almost the instant the planet was habitable. It didn't take billions of years of trial and error. As soon as the water cooled and the chemistry was right, life appeared.
Exactly. It seems that if the conditions are right, life might be not easy, but perhaps a common outcome of planetary chemistry.
And what are the theories on how it happened?
Well, the most popular one currently is the hydrothermal vent theory. Deep underwater, where volcanic heat meets cold ocean water, you get these chemical chimneys. They're constantly spewing out a rich brew of minerals and chemicals. They provide heat, they provide chemical gradients, and the rock structures themselves have tiny pores and pockets that could have acted as primitive cell walls, concentrating the chemicals needed. It's a perfect little incubator.
Then there's the RNA world theory.
That addresses the classic chicken and egg problem of DNA and proteins. You see, DNA holds the instructions to build proteins, but it needs proteins to replicate itself. So which came first?
Right.
The idea is that before DNA, we had RNA. It's a simpler molecule, but it's very clever. It's capable of both stirring information, like DNA, and acting as a catalyst to drive chemical reactions, like a protein. So it could, in theory, replicate itself, a precursor to life as we know it.
And then there's panspermia, the idea that we're all essentially aliens.
It sounds like science fiction, but it is scientifically valid. We know for a fact that asteroids and comets carry amino acids and complex organic compounds. The theory suggests that the seeds of life, or at least the molecular starter kit, arrived on those rocks during the Late Heavy Bombardment. We didn't necessarily have to start from scratch here. We were seeded from space.
Whichever way it started, the dominant life form was simple, bacteria. And for a very, very long time, that was it.
For an astonishingly long time. Billions of years of just slime. But one particular group of bacteria changed the world forever. Cyanobacteria.
They figured out a new trick, photosynthesis.
The ability to eat sunlight. A revolutionary invention. They took carbon dioxide from the atmosphere and water, used the energy from the sun, and produced sugar for themselves. But in doing so, they released a waste product.
Oh.
A poison.
Oxygen.
Oxygen. Today, we think of oxygen as life-giving. We panic if we don't have it. But back then, it was a weapon of mass destruction.
It was the first great pollution crisis.
It was. The great oxygenation event around 2.4 billion years ago. The life that existed before this was anaerobic. It didn't need oxygen, and in fact, oxygen was highly toxic to it. As these cyanobacteria pumped more and more oxygen into the oceans and the atmosphere, they essentially poisoned the planet for almost everyone else.
A mass extinction caused by life itself.
The very first one. It wiped out the vast majority of the anaerobic microbes that had dominated the world for over 1 billion years, but it cleared the path for us. Oxygen allows for high-energy metabolism. You cannot have complex animals, you cannot have brains without the high-octane fuel that is oxygen. Life changed the planet, and in doing so, it forced life itself to evolve in a completely new direction.
While life was fighting this huge chemical war, the surface of the Earth was not sitting still. We need to talk about the engine that's running beneath our feet. Plate tectonics.
This is another feature that seems to be unique to Earth, as far as we know in our solar system. Mars doesn't have it. Venus doesn't really have it. Earth's crust is cracked into these massive plates that float on the hot, flowing mantle beneath.
And what's driving them?
The heat from radioactive decay in the core. It creates huge, slow-moving convection currents in the mantle, a bit like boiling porridge, that drag these plates around the surface of the planet.
And this movement creates the dance of the continents. I love looking at maps of the ancient Earth. It looks so foreign, so alien.
It's a very slow dance, but a dramatic one. Continents crash together to form supercontinents, then they get insulated from below, heat up, and rip apart again. We all know Pangaea, the most recent one, about 335 million years ago when the dinosaurs were just starting out. But before that, there was Rodinia, about 1 billion years ago, and it's still happening right now. The Atlantic Ocean is getting wider by about 2.5 centimeters a year, about the same speed your fingernails grow. And if you project that forward, in about 250 million years, we predict a new supercontinent will form. Some call it Pangaea Ultima. The map of the Earth is temporary. We just live in a snapshot of a very long movie.
And tectonics does more than just move the land around, though. It's a kind of planetary recycling system.
That's a crucial point. It acts as a global thermostat by recycling carbon. Volcanoes, which form at plate boundaries, spew carbon dioxide into the atmosphere, which keeps the planet warm through the greenhouse effect. But then, weathering of rocks pulls that carbon dioxide out of the air, it gets washed into the oceans, and eventually gets dragged back down into the mantle at subduction zones.
So it regulates the temperature.
It does. It's a long-term feedback loop. Without plate tectonics, Earth might have turned into a Venus-like hellscape with a runaway greenhouse effect, or a frozen Mars with no atmosphere. It keeps the temperature in that habitable, just right range over geological time.
So we have a stable climate, we have oxygen, we have moving continents, but for billions of years, life was still just single cells. It's astonishing how long the delay was. 3 billion years of, well, not much happening.
It is. Geologists even call it the boring billion. Life was just stuck in a rut. It was there, but it wasn't getting complex. But then, around 600 million years ago, the dam broke.
The Cambrian explosion.
The most significant turning point in the history of biology. In a geological blink of an eye, a window of just about 25 million years, almost every major animal group, what we call a phylum, appeared in the fossil record. The ancestors of everything we see today. Eyes evolved, legs, shells, claws, jaw.
Why then? What changed after waiting for so long?
It was likely a perfect storm of factors. Oxygen levels in the atmosphere finally hit a critical threshold, high enough to support larger bodies and more active metabolisms. Another key innovation was the invention of predation. Animals started actively hunting and eating each other.
Which would drive an evolutionary arms race.
Precisely. You suddenly needed armor for defense, you needed speed to escape, you needed better senses to find prey, and genetically, life developed a new toolkit, the Hox genes, which are like master control switches that allowed for complex, segmented body plans to be built for the first time.
And from that point on, the timeline just accelerates wildly, doesn't it? We go from the first fish to amphibians crawling onto land around 375 million years ago, then the dinosaurs emerging around 230 million years ago. They ruled for ages.
For over 150 million years, and then gone. That asteroid, 66 million years ago, ended their reign and opened the door for the mammals who had been hiding in the shadows.
And then very, very recently, us. It's just the blink of an eye. Human ancestors split from other apes around 7 million years ago. Homo sapiens, people like us, only appeared on the scene about 300,000 years ago.
To put that in perspective, if you compressed Earth's entire 4.6 billion year history into a single 24-hour clock, humans appear in the last second before midnight. We are incredibly, profoundly new.
It makes you wonder, looking at all these specific events, the collision that made the moon, the magnetic field, the tectonics, just how lucky we are. We often talk about the Goldilocks zone in terms of distance from the sun, but it's so much more than that, isn't it?
It's a Goldilocks everything. We really did win a cosmic lottery with multiple winning numbers. Yes, we're the right distance from the sun for liquid water to exist. But look at all the other factors.
Like the size of the planet.
Exactly. We're the right size. Big enough for our gravity to hold onto a substantial atmosphere, but not so big that we became a gas giant like Jupiter. We have the magnetic field to shield us. We have the large moon to stabilize our climate.
And we have Jupiter itself.
The unsung hero of the solar system.
Yeah.
Jupiter's absolutely massive. Its gravity acts as a sort of cosmic vacuum cleaner. It attracts or deflects many of the asteroids and comets that might otherwise head for the inner solar system and hit Earth. Without Jupiter standing guard out there, complex life here might get wiped out by major impacts every few million years.
It's just this precarious stack of variables. If you remove any one of them, take away the moon, shrink the planet, turn off the magnetic field, we aren't here having this conversation.
We're not.
Oh.
And when you look at the sheer scale of what we are standing on, the mass of the Earth is nearly 6 septillion kilograms. The core is as hot as the surface of the sun. We are living on this thin, fragile crust over a churning engine of molten rock, protected by a bubble of air spinning in an infinite void. It really is a miracle of statistics.
And yet, as durable and as ancient as the Earth seems, it is finite. The biography has a final chapter.
It does. Nothing lasts forever, not even planets. The sun is a star, and stars have life cycles. It's gradually getting hotter as it ages. In about 1 billion years, the sun's luminosity will have increased enough to boil away Earth's oceans.
1 billion years. It sounds like an eternity, but on a geological scale.
It's the final act. The planet will become a dry, sterile rock. And then, in about 5 billion years, the sun will run out of its main hydrogen fuel. Its core will collapse, and its outer layers will expand into a red giant.
And it will swallow the inner planets.
It will likely engulf Mercury, Venus, and probably Earth itself. The planet will be vaporized, returning to the cloud of stardust from which it came.
Dust to dust on a planetary scale.
Precisely. But that is the deep, deep future. The more pressing concern, I think, is the immediate future.
The human impacts.
We have become a geological force of nature now. We are moving more sediment with our construction and farming than all the world's rivers combined. We are changing the chemistry of the atmosphere faster than the volcanoes ever did. We are driving species to extinction at a rate that is perhaps 1,000 times the natural background average.
It's a strange paradox, isn't it? Earth survived the Hadean fire, the Theia impact, the bombardments, the ice ages. It is an incredibly tough and resilient system. But the specific conditions that support us, our civilization, our agriculture, our coastal cities, those are fragile.
That is the crucial distinction. The planet will be fine. Life in some form will likely be fine. Bacteria and insects are very resilient. But we need a very specific, narrow range of conditions. We evolved in the stable climate of the Holocene, and we are the ones dismantling it.
We have been here for 0.000065% of Earth's history, and yet we have managed to alter its trajectory.
Which brings me to the overview effect. That profound shift in perspective that astronauts talk about when they see Earth from space.
I've always been fascinated by that.
It's a profound psychological shift. When you leave the surface and look back, you don't see the borders on a map. You don't see economies or politics. You see a pale blue dot, a tiny, fragile, living biosphere suspended in an infinite hostile blackness. They say it changes you forever.
You realize that this is it.
This is it. There is no backup drive. There is no planet B, not anytime soon.
Carl Sagan's sentiment always comes back to me. It is the only home we've ever known. Every person you have ever loved, every war ever fought, every hope and every dream happened on this little mote of dust.
And that perspective brings with it a very heavy responsibility. If Earth spent 4.6 billion years perfecting these conditions, filtering the air, stabilizing the climate, evolving the incredible complexity of the biosphere, and we are the first species with the conscious power to undo all of that, what is our role?
Are we the stewards? Are we just a brief, failed experiment in intelligence?
That is the question of our time, isn't it? Intelligence is a powerful evolutionary tool, but it's incredibly dangerous if it isn't coupled with wisdom and foresight. We know the history now. We know the story of the stardust. The question is whether we can write a good next chapter or if we will just be a short, strange footnote in the geological record.
It changes how you look at the sky, doesn't it, knowing all this?
It does, and it changes how you look at the ground beneath your feet.
So as we close this deep dive, I want to leave you with that thought. You are standing on a miracle, a 4.6 billion-year-old vessel that survived hellfire and ice to give you a home. It is, as far as we know, the only place in the universe where the universe can think about itself. What are you going to do with it?